Hello everyone and welcome to this video. So I've been getting a lot of questions about the space physics past papers. So I remembered that the playlist which has been uploaded like a year ago, it doesn't have any past papers to it. So this is a test that I conducted for my students at school and in my tuitions in my personal classes. So that's something which will give you an idea of how questions are to be done. For example, question number 1. So average distance from Earth to the Sun is given. What is the orbital speed of the Earth? If this is the distance, then this is the radius. And you know that the formula for the average orbital speed is 2 pi r over t. This is just r, so that's 2 pi. But if I look at the units for the answers, that's kilometers per day. So first I would have to convert this to kilometers by dividing by 10 to the 3. So that becomes 1.5, and using rules of indices, this would be into 10 to the 8 divided by the time. So the time taken for one orbit is 365 days. If it was asked in the classic units of meters per second, I would convert, but because this is in the time of days, I'll just let that go into this equation and I'll calculate this. So this turns out to be option C. Let's go on to the next one. So this one says a planet in the solar system is at the point in the orbit where it is closest to the sun. Which row is correct? If it's closest to the sun, then we know that because of the gravitational pull being the greatest, its speed would be the greatest. So it's either of A and B. And the energy in the GPE store. So we know that just as the energy in our classic formula GPE, it's equal to mgh. So the greater the height above the floor or whatever reference we have, the greater the GPE. Similarly, the greater the distance from the sun, the greater the GPE. So if it's closest to the sun, that means the distance is at a minimum. So the GPE is also at a minimum. So that's B. Question 3. Diameter of the Milky Way is approximately 100,000 light years. What is this distance in meters? So this is a more tricky MCQ because for IGCSE you are supposed to memorize that 1 light year, what's the value of that. But if you are an O-level student, then you will just need to work this out on the spot. So 1 light year is the distance traveled by light in 1 year. So that's a simple application of this formula. So speed is 3 into 10 to the 8. Time is 1 year is 365 days. Each day is 24 hours. Each hour is 60 minutes. Each minute is 60 seconds. So when you do this, this turns out to be 9.5 into 10 to the 15. That's the value of 15, not 5, 15. So that's the value of 1 light years. So if you have 100,000 light years, so this would also be multiplied by 100,000, which is basically 10 to the 5. So that turns out to be D, right? Base is the same, powers are added. Next, which statement about the sun is correct? The nuclear reactions in the sun create mainly radio and micro. This is not true. We know it mainly creates 3, which is UV, visible light, and infrared. Sun is powered by fission reactions? No. It's powered by fission reactions? No. It's powered by fusion reactions in which hydrogen nuclei are fusing to give us helium, and the EM radiation, the 3 main regions we just talked about. So a student spills ink on the page in a textbook that defines redshift. Ink covers 3 important words, 1, 2, and 3. So redshift is the dash in the observed dash of EM radiation from dash stars and galaxies. Now you know one possible answer could be it's the increase in observed wavelength, right? Or it could also be a decrease in the frequency. Yeah, because that's what redshift means, that all the wavelengths are shifted towards the red end, right? So increased wavelength. So increased wavelength is also correct. Decreased frequency is also correct. But you know, this tells us that the stars are receding, they are going away from us. So that's option C. Next, question number 6. Which list shows the planets in order of increasing distance from the sun? So you know the mnemonic MVEM JSUN, right? So Mercury, Venus, Earth, Mars. So that's C. Jupiter, Saturn, Uranus, and Neptune. What is never formed by the explosion of a red supergiant? A red supergiant is a stage of a high mass star. So high mass stars can possibly form black holes, neutron stars. In the supernova stage, they also form new heavier elements, but they never form a white dwarf. This is something associated with low mass stars. Question number 8. A student writes 4 statements about the solar system. So light takes approximately this many seconds to travel from sun to the earth. This is not true. We should know that this value is 500 seconds. The earth approximately takes 24 hours to rotate on its axis once. This is true. So any option that doesn't contain 2 would be wrong. So it can't be D. Moon takes approximately 1 month to orbit the earth. So the moon takes approximately 1 month to orbit the earth. This is correct. The sun takes approximately 365 days to orbit the earth. It's the other way around. The earth takes 365 days to orbit the sun. So it's 2 and 3. So that's C. 9. Which statement about the life cycle of a star is correct? All stars eventually run out of hydrogen as fuel. This is correct. A red giant forms a planetary nebula with a supernova at its center. This is not true. It's with a white dwarf at the center, which eventually cools down to a black dwarf. C. A white dwarf star eventually forms a black hole. Not correct. Most stars expand and form protostars. So stars do expand, but not in this stage. When it collapses under its own gravity, that's when we say a protostar is formed. Question 10. Which statement is correct? Orbital speed of the earth around the sun is given by this expression, 2 pi times average diameter. No, it's supposed to be the average radius. Orbit of the sun around the earth around the sun is an ellipse. This is true. Moon takes approximately 1 month to orbit the sun. No, it orbits the earth. Light from the sun takes 5 minutes. Again, no, it takes 500 seconds. So that's B. Let's go on to the structured questions now. 8.1 shows data about 3 planets, Mercury, Venus, and Earth. So you have the time for one orbit, distance from the sun, average density, and gravitational field strength at the surface. 8.1 shows these planets in alignment. They rotate around the sun in the direction shown. Mark and label on 8.1 the position of the 3 planets 110 days after the position shown in 8.1. Alright, so in 110 days, all we need to do is we have the time period of each of these. So we need to see where the planets, all of these would be. Alright, so let me just do something here to make the orbits clearer. Let me make a few circles here. So like this is one orbit. So like this is one orbit. This is for Mercury. Let's do the same thing for Venus. Like this, and the same thing for Earth. Alright, so this seems fair enough. Let me just get rid of the shading here. Okay, so for Mercury, we know that it completes one orbit in 88 days. So that's actually less than 110. So I know that 110 minus 88, because in 88 days it would just be back here, right? So the excess time over the 88 till 110, which is 22, right? So 22 days are in excess. So 22 as a fraction of its time period, which is 88, is the excess. So it would cover a angle in direct proportion. So this gives us the angle that it would cover, right? So 22 is the time period, that is the time that it took apart from the 88. So 22 is the leftover from the 110 minus 88 as a fraction of the time period, because in one time period it does 360 degrees, one full revolution. So this would give me the excess angle that it covers. So if I just try to find this out now, this turns out to be So that's a quarter. So multiplied by 360, this gives us 90 degrees. So it would have gone 90 degrees. So the new position of Mercury would be here. Let's call this M. In fact, let me use blue for this. So this is M. Then for Venus, I do the same thing. Now Venus, it takes a time of 220 days for the orbit. 110, after 110 days, this means it would have only completed half of the orbit. The math will also tell me the same thing. So 110 as a fraction of the time period times 360 would be 180 degrees. So that's only half. So this means now it would be here. This is for Venus. Then for Earth, so 365 days is the time for Earth. So 110 days after, we can again just use proportion to see how much time, how much angle it would have gone through. So 110 over 365 times 360. Let's work this out. So 110 divided by 365 times 360 is 108 degrees approximately. So 108 would be somewhat more than 90. So probably someplace here. Again, you don't have to actually measure this. The calculations should be clear as to how you've reached your answer. So this is the position of the Earth. All right. Each of these planets has a similar average density, suggests why the gravitational field strength at the surface of Mercury is much smaller than at the surface of Venus. All right, so this is shown in this table here that all of these have a more or less average density that's almost equal, 5400, 5200, 5500. So why is the gravitational field strength so different for all of these? So we know that the density formula, density is given by mass over volume, and naturally as we go out, this is also something you can see from the diagram, Venus is larger, right? Venus is larger than Mercury. So because it's larger, its mass must also be more for the density to be almost the same, right? So if its volume is larger, its mass would also be larger. That means that Mercury has a smaller mass. So that's what you would say, that Mercury has a lesser mass. All right, so what you need to know about gravitational field strength is this, that the gravitational field strength is basically proportional to the mass of the planet and inversely proportional to the radius squared. So basically this factor here outweighs this factor, that even though it's smaller in size, its mass is so less that the gravitational field strength is also really less. Part 2, an object has a weight of 37 Newton on the surface of Mercury. Calculate its weight on the surface of the Earth. Show your working. Okay, so if weight is given on Mercury, so that's 37. I know mass would be the same. These are ideas from mass, weight, density. And from the table, I can get small g, which is 3.7. So from here, I get the mass as 10 kg. And then this I can use for the weight on Earth. So that's mg again. So that's 10 times 9.8. So that turns out to be 98 newtons. Part C, state what is meant by a moon. So we know that this is a natural satellite. But what's important to say is that orbits a planet. All right. So this is what you say for the moon. Next part. So for the sun, we know that it's not a high mass star. This is something your syllabus tells you, that it's actually a smaller, or what would be called a medium sized star. It's called a yellow dwarf. So when we talk about the sun, we know that it's the steps that would follow for a low mass star. So as hydrogen runs out, we know that it would first become a red giant when it expands. And you know why this is so. right? Because the hydrogen, when this runs out, so even helium starts fusing together, so it becomes a red giant, and then gradually it forms a planetary nebula as the gases are expelled with the white dwarf at the center. So that's what you have to say. Again, you just have to basically name the stages. That's something which is more important. It's not really explaining how this is happening, because that's not what the question asks. So you don't really have to say in this part that why it expands because of helium fusing together, creating an even greater outward force. So that all of that is correct, but you didn't have to say that in this question. Let's go on to this one. This is question number 2. So basically the second structured question and the last question of the paper overall. Stable star in a distant galaxy has a mass that is more than 15 times the mass of the sun. So we know this is a high mass star, right? So usually we say that whenever a star has 8 times the mass of the sun or more, that's a high mass. So this is 15 times. This is obviously high mass. So what this one says is, so the first part is just asking about the nuclear reaction which happens. So you know this reaction is called nuclear fusion, right? So you will say that hydrogen nuclei fuse together. Okay, so it also says give the name of the reaction, right? So I'm going to write this in brackets, nuclear fusion, to produce helium nuclei. Again, that's really all this question asks for. You don't need to say why the high temperature is needed or anything else unless the examiner asks that. So basically nuclear fusion, saying that it's hydrogen nuclei as the ingredients and helium nuclei is the product, right? And this basically releases energy. So let me also write this, energy. Explain how this nuclear reaction helps to keep the star stable. We know this in terms of the what do you call it, the forces which are required. This is something that we talked about a lot in the videos in class as well. So we know that this reaction produces energy, which basically creates that high temperature. So the outward force due to the high temperature and again you can also say high pressure is balanced by the inward force due to gravity. All right, so the attractive force which is holding the star and the outward force because of the high temperature produced by the nuclear fusion reaction, those are equal. As a massive star approaches the end of the life, it stops being stable and becomes a red supergiant, state why the nuclear reaction can no longer keep the star stable. So stability is in terms of the balance between these two forces. So you know that as hydrogen runs out, outward force decreases. So they're no longer balanced. Describe what happens then to the red supergiant. So for the red supergiant, we know that the red supergiant explodes. So this is onwards from the red supergiant stage. So that's why I'm just picking up from where the examiner has given me the scenario, and turns into a supernova. So I would then say there is a large increase in temperature, which causes the production of heavier elements. As the gases are expelled in a nebula, then you will say that it can form either a black hole or a neutron star. Depending on the mass of the star. All right, so that's this complete response, and this was basically a test question that we did. If you got all of this correct, amazing. If not, then you'll probably need to go back and revise through the videos again. All right, so stay tuned. I'll be uploading more videos. Like, comment, subscribe. Let me know if you have any other videos that you'd like to see next in the comments. So yeah, so just stay tuned to the channel. I'll be uploading more cool stuff. Bye.